So this part of the hough, generalized hough transform, I'm going to be talking about rotation invariant. So what happened if if the object you're looking for is in your R table and is in the image space, but is rotated? How would you find that object? Clearly it's there, it's just rotated. With the algorithm that I showed you in the previous video for generalized hough transform, you will not be able to find that object if it's rotated, because now all the angles are off, because all your thetas are off, so your R table would just take you to an entirely wrong place and it would not be able to recognize that object, even though it's there. So now I'm going to talk about rotation invariant and address how we'll be able to detect the object if it's rotated. The idea is actually kind of retarded. Well, retarded in the sense that it's kind of duh. Of course, that's how you would do it. You simply find the angle that the object is rotated, and you subtract that angle. That's it. So if you are looking for that blob that you're looking for, and the blob is rotated by 30 degrees on the image, you take that blob and you subtract 30 degrees to make it horizontal or exactly in the same orientation as your R table, and then you try to see if that's your object. And that's all there is to it. Actual implementation is hard, because how do you know it's 30 degrees, and how do you know you should be rotating there? So in actual implementation, you'll actually have to try all the possible degrees on all the possible pixels to see whether whether that object is there, and if that object has been rotated, and what degrees that object has been rotated. So that's actually implementation detail that I might have an opportunity to go into detail. But for now, let's talk about how rotational invariant actually works. So I have an example here. This example, it is a simple square. It's a black square and white background. So what happens is that the gradient is going out. So you can see that in this case the gradient is 90 degrees. So we have this gradient that's going out, and then this is going in. So the vectors are going in to the centroid, which is the reference point. And here I have a simple R table, and in the simple R table, what I have is these three, which is at 0 degrees, and that's the gradient. And now I have three vectors, these three vectors, which records the alpha and the magnitude for each of these points. And I have a 90-degree vector that record each of these points, these 2 points. That's here. Okay, so now I'm searching for this square, but now the square is rotated. So it's actually a diamond. So here inside this diamond, I have 3 reference points, but I noticed that this diamond is simply a rotation of the square and rotated by 45 degrees. So what I do is I find the gradient of this vector and I simply minus 45 degrees from it. So I subtract 45 degrees because this diamond is 45 degrees rotated from the square. So what I would do, if I can find my Sharpie, which I was just holding on to earlier, where is it? Damn it, right here. Okay, So what I would do is, for this vector, I would rotate it by 45 degrees. And now, this vector will be at 0 degrees. So now I go to this table, and I look for this vector. And this vector would aim at 3 directions. Oh, right. So here in this table, I have 3 vectors. So at this point, I have 3 vectors. And I go here, and this is another 45-degree gradient, which I again have to subtract 45 degrees because it's rotated by 45 degrees. So I'm at 0 degrees. And at 0 degrees, I have 3 vectors. So again, I have to try out all 3 of these vectors. And here you can see that this vector, those 2 vectors overlap. So this is a possible reference point. And here, I have to look at this vector. Now this vector is around, the gradient of this vector is around 135 degrees. And we subtract 45 degrees from this, and then that would give us 90 degrees. So I go to this table, and I see 2 vectors. So I do one vector, this vector, and I do this vector. So now I have 3 volts on this point. So here, this point, from the 90 degree, this one from the 0 degree, and this one from 0 degree. So now I have 3 volts on this point for these 3 vectors. So now I recognize that this is indeed my reference point, and this object has indeed been found, and it's simply rotated by 45 degrees. So that's how I'm able to recognize this. And if I have a piece of noise here, and this noise has a gradient of also 135 degrees, and if I were to try these 2 vectors, it's not going to vote on this point because the magnitude information recorded here doesn't take me to here. So that's how I know this is redundant information. And that's the basic idea for dealing with rotation, invariant, and generalized Hough transform. So you simply find the angle of rotation, and you subtract out that rotation, and you do everything the same. So what makes sense now is to talk about scale invariant, and I think that should be talked about on Wednesday.